The morning after the storm, every man in the valley walked the same path. They passed broken fences. They passed collapsed sheds. They passed 3 square-walled cabins with their roofs peeled back like tin lids, timbers scattered across frozen ground, hearthstones cracked clean in half. Then they stopped. At the far edge of the clearing, something stood untouched. No broken beam, no shifted wall, no cracked mortar. The structure sat in the same landscape that had just swallowed everything around it, and it looked impossibly like the storm had chosen to go around it. The temperature had dropped to 11 degrees Fahrenheit overnight. Wind gusts had hit near 60 miles per hour. And yet, when the door opened, the air that came out was warm. Not barely warm. Warm. One man reportedly stepped inside, pressed his palm flat against the inner wall, and said nothing for a long moment. The wall was still radiating heat. Hours after the fire had died down to embers. The neighbors had laughed at the builder when he started. They said he was wasting brick. They said a round structure couldn't hold a proper roof. They said no sane man builds without corners. They weren't wrong to be skeptical. A round cabin looks impractical. It wastes lumber cuts. It demands more skill from the mason. Nothing about it resembles the standard frontier cabin of the 1800s. The rectangle, the familiar box, the shape every settler trusted. But something about that shape, that continuous, cornerless ring of brick and stone, had done something the square walls never could. And the strange part? The secret wasn't obvious. Not even to the men standing inside it that morning, running their hands along warm brick, shaking their heads in silence. The answer wasn't in the firewood he used. It wasn't in the quality of his mortar. It wasn't in the thickness of his roof. It was in something most of them had never thought to think about at all. If you've ever wondered why some old structures seem to defy the logic of winter, subscribe and drop a comment telling us where you're watching from. We want to know if you've ever seen anything like this near you. His name was Eldon Marsh. He wasn't an architect. He wasn't an engineer. He hadn't studied at any institution that would have given him a certificate to hang on a wall. And even if he had, there wouldn't have been a wall with corners to hang it on, because Eldon Marsh had decided, sometime in the winter of 1871, that he was done building rectangles. Local accounts from Harlan County, Kentucky, describe him as a solitary man, the kind who spoke slowly and listened longer than most people were comfortable with. He had come to the Appalachian foothills from Western Virginia as a young man, working first as a farmhand, then as a stonemason's apprentice, and eventually setting out on his own with a mule, a set of hand tools, and a reputation for being particular about the way things were built. He had built square cabins before, several of them, and he had watched, winter after winter, what those cabins did under pressure. He watched the corners crack first, always the corners. When wind hit a flat wall at speed, it built pressure against the surface, and then found the corner, where 2 flat planes met at 90 degrees, and that junction became a point of concentrated stress. The mortar there would develop hairline fractures. The logs would begin to separate, just slightly, just enough to let a needle of cold air through. And that needle, over the course of a long winter night, would become a constant, invisible drain. He had also noticed something about heat. Inside a square cabin, the fire built its warmth and pushed it outward, but the corners caught cold air and held it. You could stand 3 feet from the hearth and feel the radiant heat on your face, then turn and take 2 steps toward a corner and feel the temperature drop by what felt like 10 or 15 degrees Fahrenheit. The corners were cold pockets, dead zones, places the heat couldn't fully reach without being fed constantly. In the winter of 1869, oral accounts suggest Eldon spent a particularly brutal January in a small square cabin near the Cumberland Gap. He burned through what he estimated was 40% more firewood than the previous winter, and still woke most mornings to frost on the inside of the walls near the corners. He lay awake listening to the wind press against the flat faces of the walls and thought, with the particular clarity that comes from serious cold and a near-empty woodpile, that the shape of the building itself was the problem. He started drawing in the spring. Not on paper. Paper was scarce, and he didn't trust drawings that blew away. He drew in the dirt outside his workshop with the blunt end of a hickory stick. Circles. Circles of different sizes. He would crouch over them for long stretches, tracing the curve with his finger, measuring the diameter with a length of rope, imagining the lines of wind pressure flowing around the exterior rather than stacking against a flat face. By the summer of 1871, he had a design, not a blueprint, a vision. A continuous ring of locally quarried sandstone at the foundation, rising in a hand-laid brick, tapering toward a conical timber roof. No corners, no flat wall long enough to give the wind a target. A structure that would offer the same curved surface to the storm no matter which direction it came from. He told two men about the plan. One laughed. The other said he admired the ambition but wouldn't want to be inside it when the roof came down. Eldon Marsh went home, sharpened his chisels, and began to gather stone. The skepticism wasn't unreasonable. It's worth saying that clearly, because the easy version of this story cast the community as fools and Eldon as a misunderstood genius. But the men of Harlan County in the early 1870s weren't stupid. They were practical. And from a purely practical standpoint, building round made very little sense. Consider the lumber problem first. Every plank, every beam, every floorboard cut from a straight tree comes out rectangular. Fitting rectangular lumber into a circular structure meant cutting angles into every piece, wasting material with every pass of the saw. A standard square cabin of that era, roughly 16 by 20 feet, could be framed and floored with minimal waste. A round cabin of equivalent interior area required cuts that produced curved offcuts most craftsmen consider garbage. In a region where sawmill access was limited and would have to be hauled or felled by hand, waste wasn't just inefficiency. It was a real cost. Then there was the furniture problem. Oral accounts from neighboring families mentioned this more than once, almost mockingly. How do you set a table against a curved wall? Where do you put a bed frame? A square room organizes domestic life along straight lines. Shelves, beds, trunks, workbenches all fit flush against flat walls. A round room offers none of that natural alignment. Everything floats awkwardly in the center or sits at an angle. One neighbor, a farmer and part-time carpenter named Cobb Whitfield, was reportedly the most vocal critic. According to a written account preserved in a county historical archive, Whitfield told Eldon directly that a round cabin was the kind of idea a man gets when he's been alone too long in the cold. He didn't mean it as a compliment. There was also a structural argument that seemed, on the surface, entirely logical. Corners, in a conventional square cabin, are where the walls tie together. The interlocking of perpendicular walls at a corner joint creates mutual reinforcement. Each wall braces the other. Remove the corners and what holds the walls in place? To the experienced cabin builders of the region, the answer was nothing obvious. A continuous brick ring with no corners to lock it in place looked, from their vantage point, like a wall that could simply unravel. Even the roof presented a problem the neighbors were quick to point out. Cutting a flat-sided roof to cover a rectangular cabin was a skill every competent carpenter understood. Cutting a conical or rounded roof to cover a circular footprint required geometry that most frontier craftsmen had never been asked to produce. The rafter angles had to be calculated differently. The peak had to distribute load radially rather than along two parallel ridge lines. It looked complicated because it was. So the laughter wasn't cruelty for its own sake. It was the sound of experienced men looking at a plan that violated every familiar economy of frontier construction and concluding, sensibly, that it would fail. What they couldn't see, what none of them had the framework to calculate, was what a curved wall actually does when the wind hits it, or what a room with no corners does to the heat that rises from a fire at its center. The physics hadn't been explained to them, and Eldon Marsh didn't have the words to explain it either. He had something better. He had already decided to build it. To understand why the round cabin worked, you have to understand what corners actually do to a building in winter, and the answer is more violent than most people imagine. Start with wind pressure. When a sustained wind, say 40 miles per hour, which is not unusual in an Appalachian winter storm, meets a flat vertical wall, it doesn't simply pass by. It stacks. The air has nowhere to go except sideways along the face of the wall, and as it reaches the corner, it accelerates around the 90-degree angle, creating a zone of dramatically reduced pressure on the adjacent wall face. This difference in pressure between the windward face and the leeward face pulls at the structure from both sides simultaneously. The wall is being pushed inward from one direction and pulled outward from another. At the corner joint itself, where two walls meet, this pressure differential is most intense. The mortar in that joint experiences what engineers would later describe as shear stress, forces pulling the joint in two different directions at once. Over time, and especially through the repeated freeze-thaw cycles of a mountain winter, that shear stress opens microfractures. The fractures allow moisture in. The moisture freezes, expands, and widens the fractures. By the third or fourth winter, what started as a hairline crack at corner joint has become a visible gap. And a gap in a frontier cabin wall is not a cosmetic problem. It is a thermal emergency. Now contrast that with what happens when the same 40-mile-per-hour wind meets a curved wall. The air has no flat face to stack against. It meets the surface at an angle and begins to flow around the curve immediately, smoothly, continuously, without the pressure buildup that a flat wall creates. The load is distributed along the entire circumference of the structure rather than concentrated at 2 or 4 corners. There is no point of maximum stress. There is no corner for the wind to pry at. This principle, that curved surfaces distribute force more evenly than flat ones, was understood intuitively by bridge builders, boat builders, and barrel makers long before it was formalized in any engineering text. The Roman arch relied on it. The barrel vault relied on it. The Dome of the Pantheon had been demonstrating it since 125 AD. What Eldon Marsh was doing in the hills of Kentucky wasn't inventing a new principle. He was applying an ancient one to a problem his neighbors had never thought to frame in those terms. The heat story is equally striking. In a square cabin, the fire at the hearth produces radiant heat that travels in straight lines outward from the source. The walls parallel to the fire receive direct radiation. But the corners, those 90-degree pockets where two walls meet, receive radiation from neither wall fully and from the fire only obliquely. They become cold traps. Cold air, being denser than warm air, pools in corners and sits there. The convective circulation that a well-designed interior needs to move warm air around the room is interrupted every time it hits a corner and stalls. In a round room, there are no corners to interrupt the flow. Warm air rises from the fire, spreads outward in all directions, reaches the curved wall, and descends along it in a continuous, unbroken convective loop. Every section of wall receives roughly the same amount of radiant energy. Every part of the floor benefits from the descending warm air. The thermal behavior of the space is, in the most literal sense, more even. Eldon's cabin, according to reconstructed estimates based on similar structures, would have maintained interior temperatures somewhere between 12 degrees Fahrenheit and 18 degrees Fahrenheit warmer than a comparable square cabin burning the same quantity of firewood, simply because the geometry of the room was working with the physics of heat rather than against it. The corner, it turns out, is where heat goes to disappear. And Eldon Marsh had simply refused to build one. The foundation went in first in the late spring of 1871, and it told you everything about how Eldon Marsh approached a problem. He didn't pour anything. He didn't use a form or a frame or any manufactured material. What he did was spend the better part of 3 weeks walking the creek beds and hillside outcroppings within 2 miles of his building site, selecting flat-faced sandstone pieces by hand, turning each one over, checking its face for consistent grain, rejecting any piece that showed signs of natural delamination along its layers. Local sandstone from that region of Appalachia typically runs in beds 3 to 6 inches thick, with a compressive strength sufficient for a single-story structure's foundation loads. What it lacks in tensile strength, it makes up for in thermal mass. Its density allows it to absorb and retain heat over long periods before releasing it slowly back into the space. He laid the foundation ring at a diameter of approximately 18 feet, an interior circle that would give him roughly 250 square feet of floor space, comparable to a modest but functional frontier cabin. The critical challenge at this stage was establishing a true circle on irregular ground. His method was straightforward but demanded patience. He drove a single stake at the exact center of the building site. He attached a length of rope to the stake, exactly 9 feet long, representing the radius of his intended circle. He tied a sharpened stick to the other end of the rope and walked the full circumference, dragging the stick through the soil to score a continuous curved line. Then he did it again, scoring the outer edge of the foundation wall, 18 inches further out from center. His foundation ring was 18 inches wide at its base, enough to distribute the weight of the brick walls and roof above it without settling into the soil unevenly. Laying a continuous curved foundation in stone requires a skill that most rectangular cabin builders of the era had never needed. Every stone had to be oriented so that its longest face ran tangent to the curve, not perpendicular to it, which would have left wedge-shaped gaps between adjacent stones. Eldon reportedly spent more time fitting the foundation stones than he spent on any other single phase of construction. Oral accounts from a neighbor who visited the site during this period describe him crouching over the stones for hours, turning pieces, swapping them, rejecting pieces that had already been carried from the creek bed, a process that seemed, from the outside, almost obsessive. What the neighbor didn't understand was that the precision of that foundation ring determined the structural behavior of everything above it. A slight flat section in the curve, even an irregularity of 3 or 4 inches over a 6-foot arc, would create a localized stress concentration in the brick wall rising above it. Eldon understood this not from textbooks, but from years of watching stone and mortar structures crack. They always cracked first where the geometry changed unexpectedly. The brick walls rose through the summer and into the early fall. He fired his own brick from local clay, using a small field kiln of his own construction. The bricks were not perfectly uniform. They varied slightly in thickness and width, which frontier brick often did, and this variation actually worked in his favor. In a curved wall, slight variation in unit size allows the mason to adjust the mortar joint width course by course to maintain the curve without forcing cuts. Eldon used a mortar mixed from local limestone-derived quicklime and creek sand, a combination that local masons of the period favored for its moderate flexibility after curing, important in a wall that would experience seasonal temperature swings of 80 degrees Fahrenheit or more. The wall rose to 7 feet at the eave line. At that height, the total brick mass of the circular wall, continuous, unbroken, no corner gaps, weighed an estimated 11,000 to 13,000 pounds. That mass was the other half of his thermal strategy, though he would not have used those words to describe it. Thermal mass is the capacity of a dense material to absorb heat and release it slowly over time. A wood-framed wall insulates. It slows heat transfer. A brick or stone wall does something different. It stores heat. Eldon's wall would absorb radiant and convective energy from the fire inside the cabin during the hours the fire burned hot, then release that stored energy gradually over the following 6 to 10 hours, long after the fire had died back to coals. The cabin wouldn't just stay warm while the fire was burning. It would stay warm while the occupant slept. The roof he designed as a low-pitched cone, framed with 16 hand-split, white oak rafters radiating from a central ridge ring. It wasn't a perfect solution. The joinery at the peak required more trial and correction than any other part of the build, but by October of 1871, the structure was enclosed. Eldon Marsh moved into his round cabin before the first hard frost arrived. His neighbors watched from a careful distance and waited for winter to deliver its verdict. The first fire Eldon Marsh lit inside his finished cabin burned for 3 hours on a Tuesday evening in late October of 1871. He didn't build it large. A modest fire, 4 split pieces of white oak, maybe 5 pounds of fuel total. He sat on a low wooden stool near the center of the room and watched what the heat did. It rose from a small hearth he had set into the north side of the brick ring. A firebox roughly 24 inches wide and 18 inches deep, its back wall angled slightly forward to project radiant heat toward the room's interior rather than straight up the flue. He had studied this design from a description he had once encountered of a Rumford-style fireplace, a shallow, wide-throated hearth developed in the late 1700s specifically to maximize radiant output into the room. He adapted the proportions from memory, working by eye and by hand, adjusting the firebox throat until the draw felt right. What he noticed that first evening was the absence of cold spots. In every square cabin he had ever occupied, you could map the temperature of the room by feel alone. Stand near the fire, warm. Take 3 steps sideways toward the wall, cooler. Move into a corner, noticeably cold, sometimes dramatically so, even with a strong fire burning. The corner cold was a constant companion of frontier winter life, so familiar that most settlers stopped noticing it the way you stop noticing a persistent sound. In the round cabin, the gradient simply wasn't there in the same way. The curved wall received radiant heat from the firebox across a wider arc than a flat wall would. Because the wall curved continuously back around toward the fire, portions of the wall on the far side of the room, which would have been in the cold shadow zone of a square cabin, were still within a roughly 180-degree radiation angle of the firebox. There was no corner to block the view from fire to wall. Number 90-degree angle, where radiation struck a surface face-on and the adjacent surface received almost nothing. The convective effect reinforced this. Warm air rising from the fire spread outward in all directions, not just toward 2 parallel walls as in a rectangular room, but radially, touching every part of the curved wall at roughly the same horizontal distance from the fire center. When that air cooled slightly against the wall surface and began to descend, it descended along the full circumference of the room, creating a slow, continuous convective loop, a gentle rotation of air that a later observer might describe as the room breathing. There were no stagnant corners where cold air could pool undisturbed. The brick wall itself began storing that heat within the first hour. Sandstone and fired clay brick have a specific heat capacity that allows them to absorb significant thermal energy before their surface temperature rises noticeably to the touch, meaning the wall was accumulating heat invisibly, loading up like a slow battery. By the time Eldon let the fire die back to coals that first night, the wall had been absorbing radiant and convective energy for 3 hours straight. He woke before dawn and pressed his palm flat against the inner face of the brick. It was warm. Not hot, warm. The way a stone feels when it has been sitting in afternoon sun. The fire had been reduced to cold ash, but the 11,000 pounds of bricks surrounding him had been quietly releasing their stored heat into the air of the room since the flames went down. He estimated, and local accounts suggest he mentioned this to at least one neighbor in the weeks that followed, that the cabin held a livable temperature for somewhere between 7 and 9 hours after the fire was allowed to go completely cold. In a wood-framed square cabin of comparable size, that figure, under similar conditions, was closer to 2 to 3 hours. The difference wasn't magic. It wasn't luck. It was mass, geometry, and the simple physical fact that heat, given a round room with no corners to lose itself in, has nowhere to hide. The winter of 1872 arrived early in Harlan County. By the second week of November, temperatures had already dropped below 20 degrees Fahrenheit on multiple consecutive nights. Local accounts from the period describe a particular cold snap in late January of 1873, the kind that the older residents would reference for years afterward as a benchmark for severity, when temperatures fell to between -4 degrees Fahrenheit and -8 degrees Fahrenheit over a stretch of 4 nights, accompanied by winds that stripped bark from exposed timber and drove snow horizontally through any gap it could find. It was not a dramatic single event in the way that history sometimes packages its lessons. It was sustained, grinding cold, the kind that doesn't kill in one spectacular blow, but wears through every weakness in a structure, every poorly fitted joint, every corner where mortar had begun to give. The square cabins in the valley showed the strain quickly. One neighbor, the same Cobb Whitfield who had been most vocal in his criticism of Eldon's design, reportedly burned through more than a full cord of firewood in a single week during the worst of the cold snap. His cabin, a well-built 16 by 20-foot log structure with a conventional center hearth, required a fire maintained around the clock to keep the interior above 40 degrees Fahrenheit. Even so, oral account from his wife describe waking to find the water bucket near the north wall frozen solid by morning. the north wall being the one that faced the prevailing wind and had, over 2 winters, developed a series of small but persistent gaps at the corner joints where the chinking had cracked and been pushed out by frost expansion. Eldon Marsh, according to his own account, relayed secondhand through a county circuit preacher who visited the area that spring, burned less than half a cord of firewood during the same week. Less than half. Under conditions that were driving his neighbors to the edge of their winter wood supplies, Eldon was maintaining a comfortable interior temperature. Accounts suggest he estimated somewhere around 58 degrees Fahrenheit to 62 degrees Fahrenheit during the coldest nights, with a fire he described as moderate. He banked the coals each evening before sleep, leaving a slow-burning foundation of oak and hickory that would hold through the early morning hours. The brick wall did the rest. The structural performance was equally striking. When the cold snap broke and neighbors made their customary circuit of the valley to assess storm damage, Eldon's cabin showed no new cracking in its mortar joints, no shifted stones at the foundation, no separation at the roof wall junction where the rafter feet met the top of the brick ring, a joint that, in square cabins, frequently opened during temperature extremes as different materials expanded and contracted at different rates. The curved wall had absorbed the wind load the same way it had in every lesser storm, distributing the pressure continuously around the circumference, offering no flat face for the wind to push against, no corner for the pressure differential to pry at. Cobb Whitfield walked over on the 3rd day after the worst of the cold had passed. Oral history from the county, recorded by a local schoolteacher in the 1890s, suggests he stood at the door of Eldon's cabin for a long moment without speaking. Then he stepped inside and looked at the walls. He asked no questions. He ran one hand along the brick, the way you test the temperature of something you aren't quite sure about. The wall was still warm. He left without saying much. But the following spring, according to the same recorded account, Cobb Whitfield pulled down the north wall of his own cabin, the one that had been cracking at the corners for 2 winters, and rebuilt it with a curved return at each end, shortening the flat face and reducing the corner angle from 90 degrees to something closer to 120. It wasn't a round cabin, but it was a man who had stopped laughing. History rarely hands us laboratory conditions. The story of Eldon Marsh's cabin survives not in measured data, but in oral accounts, secondhand descriptions, and the physical evidence of the structure itself, or what remained of it when county historians began documenting vernacular architecture in the region in the early 20th century. But the physics is not in question, and when you apply the known properties of the materials and geometry involved, the numbers that emerge are consistent with everything the oral record describes. Start with wind load. A standard square cabin wall measuring 16 feet wide presents a flat surface area of roughly 112 square feet to a direct wind, assuming a 7-foot wall height. At a sustained wind speed of 50 miles per hour, the static pressure against that flat surface is approximately 6.4 pounds per square foot, producing a total lateral force on that single wall face of over 700 pounds. That force is transferred almost entirely to the 2 corner joints at the ends of the wall, meaning each corner is managing more than 350 pounds of lateral load in addition to its vertical structural duties. A curved wall of equivalent radius, 9 feet, giving a circumference of roughly 56 feet, presents no flat face to the wind at any angle. The pressure is resolved tangentially along the curve, distributing the same total force across the entire wall rather than concentrating it at 2 points. The peak stress at any single location in the wall is a fraction of what a square corner experiences. Engineers working with curved masonry structures in the late 19th and early 20th centuries consistently found that curved brick walls could resist lateral loads 40% to 60% higher than equivalent flat walls before showing any sign of joint failure, a figure that aligns precisely with what the oral record describes. The thermal numbers are equally instructive. Sandstone has a volumetric heat capacity of approximately 40 BTUs per cubic foot per degree Fahrenheit. Eldon's brick wall, estimated at roughly 18 inches thick and 7 feet tall along a circumference of approximately 56 feet, contains somewhere in the range of 370 to 400 cubic feet of masonry material, brick, mortar, and the sandstone foundation contributing to the thermal reservoir. At a conservative estimate, a 3-hour fire burning moderate hardwood in a well-drafted firebox delivers somewhere between 60,000 and 90,000 BTUs to the surrounding structure. A significant portion of that energy, in a room where the fire has a continuous curved wall to radiate against at a relatively consistent distance, goes directly into the masonry rather than being lost through a chimney or absorbed asymmetrically by one wall while another stays cold. The result: a thermal reservoir capable of releasing between 6,000 and 9,000 BTUs per hour back into the room's air after the fire dies. In a well-sealed, 250-square-foot cabin losing heat at a rate consistent with a cold but not extreme winter night, that release rate is sufficient to maintain a temperature above 50 degrees Fahrenheit for 7 to 10 hours after the fire has gone completely cold. Compare that to a wood-frame square cabin of the same floor area. Timber framing has a volumetric heat capacity roughly 1/5 that of brick masonry. The walls store far less energy during the fire's burning period and release what little they store within 1 to 2 hours of the fire going cold. By 3 a.m., the cabin is essentially at ambient outdoor temperature. The firewood consumption difference follows directly from this. A cabin whose walls hold and recirculate heat for 8 hours after each firing needs to be fired once, perhaps twice, in a 24-hour winter period. A cabin whose walls shed their heat within 2 hours needs continuous firing, where the occupants wake up cold. Under the conditions Eldon described during the January cold snap of 1873, the difference between his firing schedule and his neighbors was, by rough reconstruction, somewhere between 55% and 65% less wood consumed per day. Not a miracle, a geometry lesson written in brick and cold air. Eldon Marsh did not invent the round structure. He rediscovered it. The way someone rediscovers fire after a long, warm summer has made everyone forget what cold means. The historical record of curved and circular vernacular architecture in cold climates is long enough to be embarrassing when placed beside the modern assumption that the rectangle is the only practical shape for a dwelling. The Mongolian gur, still in active use across the Central Asian steppe, where winter temperatures regularly fall below -30 degrees Fahrenheit, is a circular structure whose design has been refined over more than 2,000 years of hard weather field testing. Its circular felt-lined wall presents no flat face to the steppe wind. Its central hearth radiates heat to a curved interior surface that reflects and circulates warmth without the cold corner effect. Contemporary thermal studies of traditional jairs have found that a properly constructed and heated gur maintains an interior temperature differential of 70 degrees Fahrenheit to 90 degrees Fahrenheit above the outside air temperature, sustained through a night on a fraction of the fuel that a comparable rectangular structure would require. In the Scottish and Irish uplands, Iron Age builders constructed circular stone structures called roundhouses, some with walls up to 4 feet thick, that housed both people and animals through winters that drove the sea ice into the western firths. Archaeological, thermal modeling of reconstructed roundhouses at sites like Butser Ancient Farm in Hampshire, England, has demonstrated interior temperature retention of 15 degrees Fahrenheit to 20 degrees Fahrenheit above ambient after a single central fire, held for more than 8 hours without additional fuel. Figures that align with Eldon Marsh's account almost exactly, separated by 2,000 years and an ocean. The Mandan people of the upper Missouri River built earth lodges, circular, semi-subterranean structures with walls of packed earth and timber that could hold more than a dozen people through northern plains winters reaching -20 degrees Fahrenheit or colder. The combination of circular geometry, earth thermal mass, and a central smoke hole designed to manage interior air pressure produced structures that early European observers consistently described as surprisingly warm. Warm enough that the Mandan reportedly invited cold and hungry travelers inside during the worst storms as a matter of course. The pattern is consistent across cultures and continents. Where cold is severe and fuel is limited, the builders who survived longest chose curves. The rectangle won in the end, not because it was thermally superior, but because it was economically convenient. Rectangular lumber from rectangular mills, fitting into rectangular rooms required no special geometric skill and wasted almost nothing at the cutting stage. When sawmills industrialized in the mid-19th century and dimensional lumber became cheap and standardized, the curved wall became an eccentricity rather than a solution. The thermal cost, more firewood, more drafts, more cold corners, was absorbed without complaint because fuel was, for a time, plentiful and cheap. That calculation has begun to change. Energy costs have risen. Interest in passive heating strategies has grown. And a small but serious community of off-grid builders, natural builders, and thermal mass enthusiasts has spent the last 3 decades rediscovering, with modern instruments and deliberate experimentation, the same conclusions that Eldon Marsh reached by feel and observation in 1871. Curved walls work. They always have. We just found it more convenient to forget. The structure Eldon Marsh built in the fall of 1871 stood for longer than anyone who laughed at it would have predicted. County historical records from the early 20th century include a brief mention of a round brick structure near the head of a hollow in Harlan County, described by the surveyor who noted it as unusual in form, apparently residential, solidly constructed. By that point, Eldon himself was long gone from the record. Whether he died in the cabin, sold the land, or simply moved on is not documented. The oral tradition that preserved his story was itself fragmented by the time regional historians began collecting it, the kind of slow erasure that happens to men who built things carefully but left no papers. What the surveyors found, roughly 50 years after construction, was a wall still standing. Not every wall. The conical timber roof had collapsed inward at some point. Timber roofs without maintenance rarely outlast 2 or 3 decades in a wet Appalachian climate. The floorboards were gone, but the brick ring, the continuous circular wall that Eldon had laid stone by stone through the summer and fall of 1871, was still there, still plumb, still curved. The mortar joints showed weathering but no structural cracking. The foundation ring of sandstone had not settled unevenly. There were no corner failures because there were no corners. A wall built to have no weak point had, in the end, developed none. There is something in that detail that resists easy sentimentality but invites serious thought. The men who laughed at Eldon Marsh built square cabins that, by all accounts, required constant maintenance at their corner joints. They burned more wood. They woke to colder mornings. Their walls cracked where the wind and the frost found the geometry's weakest point, and they patched those cracks, and the cracks came back because the geometry hadn't changed. Eldon changed the geometry. He did it without a university education, without an engineering license, without access to the thermal physics literature that would have given him the vocabulary to explain what he already understood intuitively. He did it because he had spent enough winters inside failing structures to recognize that the failure was structural, not a matter of trying harder or burning more wood, but of building wrong from the start. The round cabin is not a fantasy of self-sufficiency or a romantic gesture toward the past. It is a solution to a specific, measurable problem. How do you keep a small enclosed space warm with limited fuel and sustained cold when the wind is working against you from every direction? The answer, it turns out, is to give the wind no direction to push from. Every culture that survived long enough in cold climates without industrial energy eventually arrived at the same shape. The GR, the roundhouse, the earth lodge, the Barabara of the Aleutian Islands, the round brick cabin in a Kentucky hollow. Different materials, different latitudes, different centuries, the same conclusion, reached independently, proven by the same brutal examiner. Winter. Modern construction has given us insulation values and vapor barriers and programmable thermostats, and none of those things are bad. But they are expensive, and they are dependent, and they require a supply chain that the men of Harlan County in 1873 did not have, and that's some of us, in ways we may not yet fully appreciate, may someday find ourselves without. When that moment comes, the most valuable knowledge will not be the kind printed in building codes. It will be the kind a man drew in the dirt with the blunt end of a hickory stick, a simple circle in the dust of a spring morning, before anyone had told him it couldn't be done. This script is produced for historical and educational purposes only. It does not substitute professional engineering or construction guidance. All thermal and structural figures are plausible reconstructions based on known material properties and historical accounts. They do not represent laboratory-verified measurements of specific structures.